Hello and welcome. In this work example, we're looking at a little bit of electricity calculations, starting with define the Coulomb. We use the letter Q for charge, and Coulomb is the unit of charge. And so the quantity charge is equal to the intensity of the current times time. So if we think about the units now, so the Coulomb is the unit of charge, coulombs of charge, and so they're equal to amps of current times seconds of time. So you kind of want to say something like that. 1 Coulomb is the amount of charge that flows past the point when a current of 1 amp flows for 1 second. Okay. We then have 2 vertical metal plates in a vacuum. They have a separation of 4 centimeters. A potential difference of 200 volts is applied between the plates. Figure 5.1 shows a side view of this arrangement. A smoke particle is in the uniform electric field between the plates. The particle has weight, 3.9 by 10 to the negative 15 newtons, and a charge, negative 8.0 by 10 to the negative 19 coulombs. The question then asks us to show that the electric force acting on a particle is 4 by 10 to the negative 15. The electric field strength, E, can be calculated as the voltage divided by the distance. We're given the voltage as 2 by 10 to the 2 volts, right? The difference between 200 and this symbol means earth or ground. So 0, so the difference between 200 and 0 is 200, divided by the separation distance, which was given us 4 centimeters, so 0.04 meters. Make sure to convert centimeters to meters because we know that a volt per meter is the same thing as a Newton of force per Coulomb of charge, right? So electric fields can be calculated either like this or like this. So once we know the value for E by dividing those two, which I will show you on the screen right here, 200 divided by 0.04. Now we know the field strength is 5,000 newtons per Coulomb. 5,000 volts per meter, same thing as 5,000 newtons of force acting on each Coulomb of charge. We don't have a whole Coulomb of charge in our electric field. We've only got 8.0 by 10 to the negative 19 coulombs. And so we multiply the electric field strength, which really tells us the amount of force acting on unit charge by the actual charge that we've got there. Then we're going to solve for the force on the particle. So the force is just E times Q, and E is 5,000 newtons per Coulomb, and Q is this. So I've got the 5,000 still in my calculator. I'll multiply by 8 by 10 negative 19. To get that, 4 by 10 to the negative 15, which is what it said the force should be. Good. It says on figure 5.1, draw labeled arrows to show the directions of the 2 forces acting on the smoke particle. So if we look at the figure here, we can see that there's a positive plate on this side. And so the rule for the direction of an electric field is how would a positive test charge move? Well, a positive test charge like a proton would be repelled by this positive plate, right? Like charges repelling each other. So if the proton moves this way and we have a negatively charged particle here, then we know that the electric force is going to be in the opposite direction. So one of the arrows that we should draw, and let me make it clear. So this was an electric field line. It does not ask us to draw that. It asks us to draw the force vector. So this labeled would be the electric force, and it also has weight. Weight acts down. So that would be the weight. And those are the 2 forces acting on the smoke particle. The question goes on to ask us to calculate the magnitude of F, where F is the resultant force acting on the particle. So if it's got 2 forces, we can do a vector sum, right? Add these 2 vectors. We have an electric force that pushes the smoke particle to the left, and we were just showing that its value is 4 by 10 to the negative 15 newtons. There's also a weight vector that acts straight down, and it's 3.9 by 10 to the negative 15 newtons. And so the hypotenuse of that right triangle will be the force. And so we'll solve this using Pythagoras' theorem. This squared plus this squared will equal f squared. So f is going to be the square root, right, of the sum of those squares, which I will rewrite over here. Equals f squared. So when we take the square root of both sides, right, we solve for f. There's my 4 by 10 to the negative 15 still in my calculator, so I can square that, add it to 3.9 times 10 raised to the negative 15. I want that quantity squared. And I want the square root of that. We get 5.59 or 5.6 by 10 to the negative 15. Which is a reasonable value based on the legs of this right triangle. It should be about the same order of magnitude, but also the longest or the largest force, right? The hypotenuse being the largest side. The angle of f to the horizontal. So they want us to calculate this angle right here. We'll call that theta. Theta is going to be equal to the inverse tangent of opposite over adjacent. So the ratio of side opposite to adjacent. (44 degrees). Which I'll show in the calculator right now. So we have 3.9 times 10 to the negative 15 on our numerator, divided by 4 times 10 to the negative 15 in the denominator. So the ratio of sides is this, back to standard form. And then the inverse tangent of that is 44 degrees. So that's the angle to the horizontal. Question then goes on to read, the electric field in B is switched on at time t equals 0 when a particle is at a horizontal displacement s equals 2.0 centimeters from the left-hand plate. At time t equals 0, the horizontal velocity of the particle is 0. The particle is then moved by the electric field until it hits a plate at time t equals capital T. On figure 5.2, sketch the variation with time t of the horizontal displacement s of the particle from the left-hand plate. It tells us it's initially at a horizontal displacement of 2 centimeters from the left-hand plate. So the whole field is 4 centimeters sort of between the two metal plates. It's starting halfway. The only thing that we have to show is the horizontal displacement, how it varies with time. In a uniform electric field, this particle is going to experience uniform acceleration. So we have to remember, what does a displacement time graph look like when we have acceleration? The slope of displacement time is velocity, right? So velocity is the rate of change of displacement. So the rise over the run, right, for a displacement time graph, that gives us velocity. But we've got accelerated motion here, right? We have a uniform electric field that is going to uniformly accelerate that particle in the horizontal direction. We also have the weight vector that's going to accelerate it in the vertical direction, but we're not considering that. We only want to consider the horizontal displacement. So remember that acceleration is the rate of change of velocity. If the slope of this graph is velocity and acceleration is a changing velocity, then we need a changing slope on this graph. That's a key idea to earn both of these marks. We know that the particle starts here at time 0, it's 2 centimeters, right? It's midway in the plate. We know that it crashes into the left-hand plate at a time t equals t, so that's a point. But don't just connect the dots with a straight line. Consider this idea that we start with a very sort of shallow slope, and then it gets steeper, and it's going to end sort of the steepest, right? So the line drawn tangent to the curve here is going to be the steepest, and it's shallower here, and the most shallow initially. And so the curve should sort of look like that. Nine marks that we just went through right there. But we're not done yet because we got question 6, which asks us to state what is meant by an electric current. An electric current is the rate of flow of charge, or the rate of flow of the charge carriers, usually electrons, but other things can carry charge too. So think about the intensity of the current as the charge over time. And so it's a rate, the rate of flow of charge. Put that all out in words though. Don't just let equations stand as your statements for these. All right, the question goes on to read: a metal wire has length L and cross-sectional area A, as shown in figure 6.1. It says I is the current in the wire, N is the number of free electrons per unit volume in the wire, V is the average drift speed of a free electron, and E is the charge on an electron. State, in terms of A, E, L, and N, an expression for the total charge of the free electrons in the wire. So if we start with N, which is the number per unit volume, then it kind of lets us know that we've got to cancel out the volume, right? So if we've got the number of electrons per unit volume, per meters cubed, then we're going to cancel out this meters cubed by multiplying it by a volume. What's the volume of this cylinder? It's the cross-sectional area A times the length L. So we can cancel out the per unit volume part of this by multiplying it by AL, the volume of our particular metal wire. These three terms give us the number of free electrons, but not the charge. It wants an expression for the charge on all of that. So in order to charge up all these electrons, we've got to multiply it by E, the charge on an electron. Now we've got a statement, an expression for the total charge on the free electrons in this particular wire. It says use that answer to show that the current I is given by the equation I equals nAve, where again, V is the average drift speed. So if we realize that the intensity of the current is the rate of flow of charge, as we just mentioned a moment ago, and Q, the total charge, is NALE, what we're doing is dividing by time. And we know that the velocity is the distance L, right? So an electron that moves through this wire is traveling a distance L in time t. And so velocity is L over t. And we can substitute that in here, right? Plug that in for L over t, and we get the equation I equals nAve. We now consider a metal wire in a circuit that is damaged. It says the resistivity of the metal is unchanged, but the cross-sectional area of the wire is reduced over a length of 3 millimeters, as shown in the figure. The wire has diameter D at cross-section X and diameter 0.69 D at cross-section Y. The current in the wire is 0.5 amp. Determine the ratio of the average drift speed of free electrons at the damaged cross-section Y over the average drift speed of the free electrons at the cross-section of the main part of the wire, X. So using the equation that we just derived, we've got the mean drift velocity, which would be equal to I over nAe. And we're going to set up a ratio where we're comparing the drift velocity at Y to the drift velocity at X. And so that's still equal to I over nAe. And so the ratio of these equations is going to be equal to the ratio that we're interested in over here. We can consider that the current isn't going to change. That's going to cancel. The number density isn't going to change because it's the same metal, so that's going to cancel. Elementary charge is the same value. And so the only difference here is that the area at cross-section Y is different. So a change in the area here is affecting the mean drift velocity. How does the area change if we change the diameter. We crush it down to about 70% of its original value. Well, area is proportional to the radius squared. So if we decrease the area to 0.69, the diameter, then we need to realize that the area goes down as the square of that. And so what is 0.69 squared? 0.4761. So a decrease in the diameter by this amount is going to decrease the area by this amount. And so when we make that substitution here, we can see that the ratio of these mean drift velocities is going to be equal to I over N, and the change is in Y, right? The damage cross section is Y. So the area here is only going to be 0.4761 A. If the diameter D gives an area A, then the diameter 0.69 D gives an area 0.4761 times that. And so here's the sort of what this proportion becomes. I'll make it a bit more clear down here. And we can start to combine things. And so we'll move this denominator back up to the numerator here. So we've got I, N, A, E, right? And then in the denominator here, we're combining this and this. And so we've got I from here and 0.4761A. The I's, N's, A's, and the E's cancel. And so it's just 1 over 0.4761. And that agrees with the thinking that we talked about, that it's only due to the change in the area that we'll see a difference in the mean drift velocity. So how much faster are the electrons moving in Y compared to X? Well, what's 1 divided by 0.4761? So we get a final answer of 2.1. So the electrons have to move twice as fast through Y in order to preserve that constant current. The question goes on to read, the main part of the wire with cross-section X has a resistance per unit length of 1.7 times 10 to the negative 2 ohms per meter. For the damaged length of wire, calculate the resistance per unit length. So there's going to be another change to the wire due to that damage that's occurred. And they mentioned earlier that the resistivity of the metal is unchanged. So resistivity is rho, and it's equal to resistance times area divided by length. Here they tell us that the resistance per unit length is a certain value. So they're telling us what R over L is. So let's divide each side by the area so that we can see that the resistivity divided by the area is equal to the resistance per unit length. We can solve this setting up a ratio just like we did here. Since we already know how the area is going to change, it's going to be the same sort of change to the resistance per unit length. So if rho over A gives a value of 1.7 times 10 to the negative 2 ohms per meter, then the same resistivity over 0.4761A, right? So we're setting up this ratio here, comparing X to Y. And so we want to know what is the resistance per unit length at Y, the damaged length. I'm going to call this resistance per unit length. I'm just going to call it X, so over X. Now I'm going to solve this for X. First, working on the left side, I can rewrite it as 0.4761A rho over A rho. That's using the same idea that for a complex fraction, A over B over C over D, we can just divide as multiplying by the reciprocal. So this is AD over BC, right? So that's a nice way to sort of think about simplifying a complex fraction down. So that's what I've done here. And the A's and the rho's cancel. And that's going to be equal to this over X. So equals 1.7 by 10 to the negative 2 over X. So if I multiply both sides by X and divide both sides by this, I find that my final answer, X equals 1.7 by 10 to the negative 2 over 0.4761. Calculator, you type it in 1.7 times 10 raised to the negative 2 divided by 0.4761, and we get 3.6 times 10 to the negative 2. So consider how changing the diameter of the wire makes the electrons go faster through it, but there's more resistance. Okay, there's more resistance per unit length. And so we're resisting the flow of charge more, forcing electrons to speed up in order to preserve that same current. We go on to calculate the power dissipated in that damaged length of wire. Let's keep in mind that we know the resistance per unit length is 3.6 times 10 to the negative 2 ohms per meter for that damaged length of wire. Power dissipated is equal to current times voltage, but voltage is equal to current times resistance. So if we substitute in IR for V, we get another equation for power, I squared R. Because we don't really know the voltage, we have to calculate it like this and make a substitution, or we could just calculate the power as I squared R. So power equals I squared R. I is given as half an amp, so we square that. And the resistance we have to calculate because we don't know the resistance. We only know the resistance per unit length. If you take care of the words will take care of you. So we know that there's 3.6 times 10 to the negative 2 ohms per meter. We don't have a meter. We've only got 3 millimeters. If you look at the problem, it tells us that the length of damaged wire, they show us on the figure, 3 millimeters right there. So if we had a whole meter of damaged wire, then the resistance would be that much, right? That much resistance per unit length. In order to cancel out the per unit length, just like we had to cancel out the volume of the cylinder, we have to multiply it by the length we actually have, right? So if there's 3.6 by 10 to the negative 2 ohms per meter, but we've only got 3 millimeters, then we'll multiply those two to cancel out meters. Then we know the ohms of resistance to plug into this equation. So we've still got our 3.6 by 10 to the negative 2 in the calculator, and we'll multiply it now by 3 times 10 raised to the negative 3. Could have just typed that in standard form, I suppose. And so that's the resistance. Right? And for completion's sake, I'll write it down. So R equals 1.07 by 10 to the negative 4. Much better omega than that one. My bad, class. No sloppy omegas in your calculations. We don't want to see them out there. Times 0.5 times 0.5 again, right? Because it's squared. And so we get a final power dissipated of 2.7 times 10 to the negative 5 watts. And remember, we were just calculating the power dissipated. So that answer goes right there. 2.7 times 10 to the negative 5 watts. That was the resistance per unit length from our previous calculation. The final part of this quiz is to consider how the diameter of the damaged length of the wire is further decreased. Assume that the current in the wire remains constant. State and explain qualitatively the change, if any, to the power dissipated to the damaged length of wire. Well, we've just gone through some working to really help guide our thinking with this. If we decrease the diameter of the wire even further, then what just happened to it is going to sort of happen more. We increase the resistance per unit length. And so by decreasing the diameter of the wire, we further increase the resistance in that damaged length. So a decrease in diameter will further increase the resistance. Resistance, that says, will further increase the resistance because power equals I squared R, and increase in resistance means more power will be dissipated. All right, if R goes up, power goes up too, because the current in the wire is remaining constant. This has been another worked example with Dr. Schleif. We'll see you next.